The idea of the blockchain is to allow economic interactions between vast numbers of people, and also that most transactions can be isolated from each other. If Alice pays Bob and Carol pays Dave, there's no need to interact between them. If they pay each other and interact with different nodes, it's possible that those two payments will occur and spread out to the network at the same time. In Ethereum, only one block or the other can be the next one after the parent block. Whereas in our system, you can take both of these, and so long as there aren't conflicting transactions, as long as it wouldn't cause a double spend, for instance, then you can add both of them to the directed acyclic graph of blocks, and then issue a join block that mentions both of them as parents. So we can take all of these blocks from all the different nodes and combine them very easily without forcing people to redo work. And then because of that, having a programming language that also characterizes its computations explicitly by sending messages on names, we can merely look at the trace of each of these computations and see that these didn't interact with each other at all. Therefore, they can commute with each other. And so it gives us an easy criterion for judging when we can combine blocks or not. A COM event is a delivery of a message from one process to another process. It's the most fundamental operation that Rolang does. You declare contracts, which are processes that stick around and receive arbitrarily many messages. And you can declare or deploy messages sent on one of these channels where there's a contract listening on the other end. When you do a deployment of a message to a particular channel and there's something listening there, it puts both of them together and then continues executing. So this idea of taking a listener and a sender, joining them together, that is a COM event. A transaction, in the sense of Ethereum, is a transfer of monetary value from one region to another one. In Ethereum, it's from one account to another one. In our chain, rather than have a single ledger that lists everybody's balances, we are able to split up the ledger into contracts that encapsulate the value. And so that's another way that we've parallelized these interactions, that even if you are both paying in Rev, they don't need to hit the same Rev contract. We use something called proof of shared lexical scope, but I won't go into that here. And so to transfer value from one purse to another one, a purse is one of these contracts that holds monetary value, costs about 10 COM events. So the claim of 40,000 was COM events per second. That works out to about 4,000 transactions per second. Right now on the test network, we're getting about 1,500 COM events per second on a single shard. To reach the 40,000 COM events, we're going to deploy many shards. So if we deployed 40 shards, that would be 60,000 COM events per second. It scales linearly with the number of shards, and so as people add more shards to the network, it will be able to process more COM events and therefore transactions per second. The simplest explanation is, yes, they are their own blockchains. Each blockchain has a mint that issues the currency that is used for staking on the blockchain. That is, the validators have to acquire Rev or whatever the staking token is and lock it up to ensure their good behavior on that chain. So if you have the root shard, that will be one blockchain, and then a child shard will be a completely separate blockchain run by different validators. That's the first approximation. Some complications in that are that in order to be considered a child shard as opposed to simply another blockchain, there's a pair of contracts, one running in the child and one running in the parent. In the parent, it's called a depository. In America, the depository for gold, back when we had gold-backed dollars, was called Fort Knox. But the idea is that there is a contract that will hold all of the value for the new token issued in the child shard. So, we will list the rev on exchanges, right? And you'll be able to buy rev for dollars or Bitcoin or Ethereum or what have you. But that's only the root shard's rev. If you have some child shard, what gives them the tokens issued here any value? Well, it's this pair of contracts that is part of that. So the depository holds all of the value that backs the issuance by the mint in the child shard. Now, to some extent, you're vulnerable to the validators of that shard. It's true that you could, you're always vulnerable when there's a large enough coalition of validators. In this case, they have the possibility to mint far more of the child shard stuff than they have backing the parent shard stuff. The default depository and mint contract keeps them pegged one-to-one. So first they would have to modify that contract, and you can go and look at what contract they're running before you transfer any money in there. If they did issue more, however, there would still be the requirement in the depository that wouldn't let them transfer more than what they put in out. So if they put 1,000 rev in but issued 2,000, only the first 1,000 of it would be honored. And after that, the remaining child rev would be worthless. So they have the potential to screw up the economics in their own subtree, but they can't affect the economics in the rest of the network. So that's the limit on the security that we have, where we can ensure that any particular neighborhood can't violate the assumptions of the rest of the network, any particular shard. In order to transfer value between them, there's a protocol. The depository and the mint contract are both watched by the set of validators. So if Alice is in the root shard and wants to put some money into the child shard, she will hand over the purse to the depository. The validators will see that transaction. They will then tell the mint to issue to Alice a purse in the child shard with the same amount of rev that she had above, minus some transaction fees. And so the value goes into the depository, which is backing the issuance by the mint. And so the value is conserved all the way down. Similarly, when she wants to take it out again, she hands her purse of rev to the mint, which burns it. The validators see that that transaction occurred. They tell the depository, withdraw this certain amount from the depository and give it to Alice. So we can move money between them, and that pairing, the depository and the mint, is what establishes the parent-child relationship between two shards. If some other token wanted to arrange the shards in a different manner, they could issue their own depository and mint in that way, and you could send messages using their system rather than the one that RChain provides. So they really are very independent shards that are connected by these voluntary relationships between parent and child, mint and depository. When she gives them the money, she also specifies a public key that the resulting stuff should be given to. So when the mint creates a purse, it wraps it in a contract that checks a signature first. It says, I am only going to withdraw money if this signature matches. And since she has provided a public key, she's the only one that has a private key. Or I guess whoever owns the corresponding private key can use it. So Alice could put money into the parent on behalf of Bob in the child if she knows his public key. Ladle is process for generating a type system. A type system is what you need in order to have any confidence in the code you've written. So a program is an expression of programmer intent. We want the code to do something, but humans are fallible. Therefore, in order to check that we wrote the thing correctly, we should express it again in a different way. A type is a crude summary of a program. And then the compiler can look, or the type checker can look at the program and look at the type and ask, do these two match each other? If they match, it says all good, go ahead. If they don't match, it says something is wrong. Either your type is wrong or your program is wrong. I don't know which, go figure it out. Here's where it's wrong. And so having a type system is the way that you come to have confidence that the programs you've written are correct. Now, on the web, JavaScript is the language to use in a web browser. There simply aren't any others that are widely implemented in web browsers. So Google and Microsoft and Facebook all were deploying web content on their websites and wanted to have some confidence in the code that they were deploying. And they found that because JavaScript only has a runtime type system, and a very weak one at that, that they had to develop their own static type system for JavaScript. So Google wrote Clojure compiler, Microsoft wrote TypeScript, and Facebook developed Flow, each at the cost of millions of dollars in order to provide a static type system for their language. Ladle is a way of taking a description of the language itself and deriving a type system. Instead of inventing one and showing that it works, you derive it from the operational semantics. And it's a very powerful type system. So the idea is that given any description of a programming language, and this is what Martin Lundfall is working on for RCON research with K-Framework. It's a language in which you can give a formal description of the operational semantics of a programming language. Given such a description, you push a button and it spits out a type system that you can then use. That program, that thing that takes the description and spits out a type system probably won't be ready in time to use for Rolang directly, but it will eventually be possible, and in the meantime we're just going to do that process by hand rather than code it up and let the computer do it for us. But we'll be using that technique to produce the type system for Rolang. The idea of the tuple space is that we have a collection of things called names. And these names are places where messages can be exchanged. You can send a message on a name, and you can send multiple messages to the same name. Many programming, or rather many message passing systems use a message queue where you will get them in a particular order as they arrive. In the tuple space, it's a message set. There's no guaranteed order that you can withdraw them from if you have multiple there. If you have a program invariant that there's only ever one message at most on the channel, then you can use that message as a mutex, a mutually exclusive access. So you would say, give me the message from this channel, and once I have it, I'll do some stuff and then put the message back. And that prevents anybody else from using the resources that you're using in that interim because they can't get hold of that one message. So we can implement all kinds of concurrency primitives using this idea of messages on channels. And that's really the source of the concurrent control, is this message passing stuff. So not only can you put messages in, but you can also put in what are effectively database queries. Each name can be thought of as identifying a table, and then the messages to it are the rows of the table, more or less. But then you can also put in queries to that table, and they will ask for data and process it and do something with it. The interesting thing about Rolang is that even if there's no data in the table, you can issue a query and then it will just hang on to the query until data shows up for it to process. And that's really what a contract is a query that says, give me all the data that's coming in on this name, and then I will handle those messages and produce more messages in turn. But the contract is just sitting there waiting for data, and whenever new data comes in, it runs and processes it. So you can have multiple contracts listening on a name, multiple data coming in on a name. They compete with one another to get access to these resources, do their processing, and send more messages out. So the tuple space is really the fundamental data structure that's being manipulated by the Rolang language.